So in steps 2 to 5, I'm going to show you how we can crush and subset these giant BGEN files that have millions of variants just down to a small subset format of it's just a smaller BGEN file size, and then how we can also convert that to a PLINK1 format, BED, BIM, and FAM files. So how we can go from these giant BGEN files, tens of gigabytes, even 180 gigabytes, for instance, just a lot of space that they take up, how we can go from those giant files, extract the variants that we need information from in a subset BGEN file, and then reformat that BGEN file into a PLINK1 format friendly file, which is like a BED, BIM, and FAM file. So that's what we're going to do. We're just going to organize the input files so that it's something we can work with, because what is heavy for one can be light for somebody else, and what's light for somebody else could be heavy for somebody else. It's all relative. So now I'm going to show you the genotype imputation data that we're going to use, little guy. We're going to check it out and see what it looks like. And that's just for this example, this is the genotype data that we're going to use. And it's also because it's in HG19 or GRCH37. And I have other videos about the human reference genomes in case you're stuck or confused. But let me just show you the ones that we're using right now. And let me show that to you right now. So if we go to the DNAnexus portal, then what we will see is under the bulk, IBD projects bulk, and then I'm going all the way down to imputation. And I'm just going to use this one over here, and I'll have other videos on these different other types here, but I'll use this UKB imputation from genotype. This one, I believe, is in HG38 or GRCH38. So this is an HG19. So this one is HG19, HG19, GRCH37. And then this one over here is HG38, GRCH38. So we're going to use, in this case, we're going to use this one here. So when we click it, we'll see they have those 4 types. We'll see that we have around 96 items, and my dates may be different from yours. The number of samples I have may be different. It all really depends on your sample information. It's also changed across projects and permissions, so it really depends on your project, the time that you accessed it, you refreshed it. There's so many other things that it depends on. So please don't worry if it doesn't look exactly like my data, or if the number of samples that you have differs. This is just what I currently have at this moment. And again, my sample IDs and your sample IDs may correspond to really different people, because UK Biobank switches it up so that we can't really transfer easily across projects. And this is all to protect patient and the private data that we have entrusted the UK Biobank with, to protect patient information. So they kind of make sure we can't really map easily across projects. Though we can have a mapping file, and that's a whole other thing. But anyways, let me just show you what this imputation looks like over here, this imputation file. So I'll just show you, we have like dot samples for the chromosomes. We have this mfi.txt files. We have this. Sometimes it may not load properly with the BGEN, BGI files. So those are some of the files that we have here. And we're going to be working with the sample files in particular. The MFI will tell us like the structure of the BGEN files. These are the indexes for the BGEN files, the BGI on top of it. And then these are the BGEN, the genotype files. So that's what we will be working with. here. And again, this is because our scores are for HG19, so we want to use this format so that it's in the same format as our score file, the polygenic score file for our trait of interest, which in this case is late onset Alzheimer's disease. And also why this conversion from the BGEN files also makes sense is because in PGS catalog calculator, as of now, what it mentions is that the supported file formats are VCF, variant calling format, the PLINK1 fileset .bed, .bim, .fam, and the PLINK2 fileset .pgen, .pvar, and .psam. And it says that compressed input is supported and automatically detected. For example, BGZip compression of VCF files or ZSTD compression of PLINK2 variant information files .pvar. So we're going to focus on in this video on the PLINK1 file set, the .bed, the .bim, and the .fam. And that's what I'm going to focus on, is how we go from the BGEN files to subset them and then convert them into these files. And it's also because that's the requirement, one of the possible requirements for the PGS catalog calculator tool as of now. So yeah, little guy, these are just some metrics on the BGEN format. So it's a compressed binary format for typed and imputed genotype data. So this is version 1.2 of the BGEN format. So, you know, the UK Biobank interim release imputed genotype data was released in this BGEN format. And you see here, so most genetic association studies routinely employ data on tens to hundreds of thousands of individuals genotyped or imputed at tens of millions of markers genome-wide. So traditional data formats based on text representations of these data, such as the GEN format output by impute or the variant call format VCF, are sometimes not well suited to these data quantities. Indeed, for simple programs, the time spent parsing these formats can dominate program execution time. So this format, this page, it describes the binary GEN format, BGEN, which aims to address these problems. It's a robust format that has been designed to have a specific blend of features that we believe make it useful for this type of study. It's targeted for use with large, potentially imputed genetic data sets. And the key features include the ability to store both directly typed and imputed data, store both unphased genotypes and phased haplotype data, and small file sizes through the use of efficient variable precision packed bit representations. And then they have a per variant compression, makes the format simple to index and easy to catalog, so they have the index files as well that are available. So the current genotype format on UK Biobank that we're working with, that genotype format is this BGEN format here. You can see under imputation, we've got the UKB imputation from Genotype, and we've got these BGEN files that we'll be working with. So here we're using imputed data. So our genotype data will be the dosage. It'll be a value between 0 and 2. Otherwise, the genotype would typically be 0, 1, or 2, just those fixed numbers. A 0 would mean that it's homozygous non-effect allele, so the individual has both copies of the non-effect allele. You know, whether it's like 2 A's or it's 2 G's or it's 2 T's or 2 C's, you know, they just will have 0 if they have from each parent the same allele, and that's the non-effect allele. It'll be 1 if from one parent they have the effect allele, and then from the other parent they have the non-effect allele. So you can think of it like that. And then a 2 is the homozygous effect allele. So from both parents, instead they have the same allele, and that is the effect allele. So whichever allele is the effect one that we're considering, that's what it means. That's what the 2 is here in the genotype data. But right now, because we're imputing it, and some of these will be probabilities of genotypes, so the values will be between 0 and 2. And of course, like the closer they are to one over the other, then you can kind of gather that it might be more of a homozygous non-effect allele, or it's heterozygous, or it can be a homozygous effect allele. So this will be more of our case. It's a value between 0 and 2 because it's imputed. So yeah, what we're going to see is that we are using the UK Biobank imputation from Genotype, genotype information, and the data field is this 22828, and in general, we can look up any of these fields online for UK Biobank. And so this is what it is over here, and the reference genome that is used is HG19, also known as the really sucky G R C H 37. That's what it will have there, GRCH 37. And you can see these are the participants, but of course our numbers will differ. But this is just how you can find out certain information on different data fields in the UK Biobank resource. And you'll notice that we will be calling this field UKB, this number, for the genotype information. So you'll notice that we also have this .sample file. So it's sample information, 1 row per individual / sample. So we have 487,409 in my data set. Again, guys, your number might differ based on your project and when it was refreshed and so on. But I'm just kind of zooming in on an example file. So for instance, we're looking at the chromosome 1, what its file is. So like we're zooming in on this file over here, for instance. And we can see that it's a text, kind of like a text file, but it's a .sample file. It accompanies the BGEN files, and it contains sample information. So the first 2 rows are the header. So this first row is the header, and this is just the metadata here. And the subsequent rows, they contain the sample ID. So these 487,409 rows here, these remaining ones, will have the sample IDs. And in our case, these will be the same. It'll have, the gender information as well. So this is important because the BGEN file itself, it does not store sample IDs. It just has the ordered genotypes. And tools like QCTool or PLINK, they use the .sample to map the genotypes to the correct participant. So this is really important to have this sample file. And when we're subsetting the BGEN files right now, we're not, in my case, I'm not going to be filtering out any samples at this moment. You can do all of that afterwards. Once you have the data and you've kind of computed things, you can always filter down the samples. My goal is just to filter down to the set of SNPs of interest, those set of variants, single nucleotide polymorphism. So I'm going to be holding on to all these samples right now for the analysis. But this is the sample files. And we also have these .mfi, .txt files. So this marker info file for the imputed data. So markers are like these genetic variants. And it's a tab delimited text file with per variant metadata. So what you can see here is that we have the variant ID information. We have the chromosome number, all sorts of information that we have. What we have here. So this is for chromosome 1. We have the chromosome 1. We have the position number. We have the variant, the reference alleles, the alternate alleles. This can be a variant ID signature, which is very common, but we'll be kind of focusing on the reference SNP ID because we have that in the score file as well. We have the position, the reference alleles, alternate alleles, minor allele frequency, the minor allele, and then the imputation information as well. It just gives imputation quality metrics like the info score, minor allele frequency, and so on. And the purpose is to provide a catalog of all the imputed variants in the corresponding BGEN file. And it's often used to filter variants, like maybe you want to filter variants with info greater than 0.8 and minor allele frequency greater than 0.01. It can also be used to map SNP identifiers if my list is in chromosome position _ ref alt format. So yeah, this is the format that we're using here. And yeah, this is the MFI files. And we have one for each chromosome. So yeah, you'll also see that we have these BGEN files here. So it's the main genotype imputation file that we are using here. It's in the BGEN format. It's compressed, it's binary. And since we're using the imputed, it's under imputation, it will have the per variant imputed dosages. So It can be expected allele counts, like 0 to 2, but it can be fractional. It can be probabilities for each genotype. And each .bgn file typically corresponds to a chromosome here. It really depends on different cohorts and different data. Sometimes they can combine them all together for all chromosomes. But here in this UKB imputation from genotype in this field here, this UKB22828, as now it kind of splits up the BGEN files for each chromosome, and these will be dosages here, which is just probabilities because this is imputed genotype data. So you can see here that we are visualizing the first few rows of the BGEN files here, then HG19, GRCH37. So PGSC calculator, it'll also make sure that we match the format of the score file for the trait. And the format of the BGEN file, it may differ based on the genotype information that we're using. So that's also very important. But you can see they have alternate IDs here. They have RS IDs, chromosomes, position, number of alleles. So sometimes be careful because if it's less than, this is just a snapshot for like this, of course chromosomes 1 begins with 1, but this is just some example of, what the format looks like for them. First allele, alternate alleles. So here we can see the first few rows of the BGEN file for chromosome 22, one of the smallest chromosomes, for the UKB imputation from genotype file. And you can see that it has alternate IDs, RSID reference SNP ID, chromosome position, number of alleles, first allele, alternate alleles. So we can typically filter either using the alternate IDs, which is just the chromosome number, then the HG19 or GRCH37, it's the same thing, that position, the reference allele, and the alternate allele. We can use that approach, or we can use the RSIDs, and since our score file has the RSIDs, we can just filter using the RSIDs, reference SNP IDs. So we will be using the RSID column for filtering, since our score file has the RSIDs. But this is just a little snapshot of the data that the BGEN file has, and it has this data, the genotype imputed dosage information across the samples for these variants. This is just the first 10 rows. And similarly, this is just the first 10 rows of, the chromosome 9 here, and we can see that it has a 0 in front. So any number that's less than 10, it'll, in this format, it has a 0 in front for the chromosome number. Just, a little heads up there. And so you will notice that there are these bgen.bgi files. So basically it's an index file for the .bgen file. So this is just an indexing file for the original BGEN files. And what it does is it enables fast random access to variants, to these genetic variants in the BGEN file without needing to scan the entire file, because those files are huge, like tens and tens and tens of gigabytes, right? So it helps with fast random access, and it's required for efficient extraction of specific SNPs or regions using the QC tool or BGENX or any other tools. So it's really helpful to have this. And I'll show a command that we'll be running, using the BGENX command to index it, a BGEN file, and then it is created really quickly. But it's a very important indexing file, and it should be found alongside the BGEN files, which it is here. So what you can see is that for each of the chromosomes, we have these 4 files, right? So suppose you want to extract a subset of SNPs and also potentially samples, but in this case, in our example, in this video, we'll just be subsetting SNPs. But in general, why we will use this is the dot sample will tell the tool which individuals are in the file so that we can include and exclude them accordingly. But in our case, we won't focus on that. But just so you know that's what the dot sample is there for. The mfi.txt will help you identify the right variant IDs and positions to extract. The .bgen will store the actual genotype dosages, because here we're using the imputed data in this example, so there'll be like genotype dosages between 0 and 2, some values. And the bgen.bgi will make the extraction nice and quick by indexing the .bgen. So if you want to talk about chromosomes, this is the information that we have, these 4 files for each of the chromosomes there.